Welcome back to the shop, everybody tuning in early. We're going to be getting back into some of this winch-bot firmware and generally just getting it moving and maybe breaking stuff, hopefully not. If you were here on yesterday's stream, that one wrapped up with kind of getting frustrated by debugging the pulse width modulation firmware. And there's the cat. And after reading the datasheet some more, it turned out that was just a misunderstanding in the numbering of the pulse width modulator generators versus the pulse width modulator outputs. Once I sorted that out, things started working out all right. What does this cat want? Once he's got it, he'll pull the string and roll out anywhere. You get right under the camera, huh? Do you want a Jason Bolt sticker? Alright, well that's pretty cute, but maybe we can get some work done. So, welcome back. I think we could use the camera to see what's going on here. So, here we are. So for anyone who's just tuning in or, oh, it looks like I was going to say, there's usually some context in the topic line, but that seems to be missing. Maybe I need to re-topic our topic line. Hey Tuco, what do you want, little guy? We're gonna have to re-USB all of the USBs. The topic line is a little bit complicated in that I have a proxy such that I can share cookies between the streaming machine and another machine that's easier to log in on. So I think I just refreshed, whoops. Tuco! That little cat gets on my nerves sometimes. That's showing up. Now it just needs to be accurate. Hey Tuco, what do you want, little guy? Which is a rhetorical question, because I know he just wants to play with something. Alright, that's good. Winch-bot motion control firmware is the current topic. So these winch-bots, they're designed to go in the corners of the room and pull a robotic camera around on nylon cords. So they're basically just little network-attached microcontrollers that have little motor controllers and a couple of local sensors. They'll have an encoder so that they can measure the actual movement of the nylon cord, and they'll have a force sensor to measure how much force is on it. For a few reasons, but the most immediate reason for that is to prevent the spool from moving if the force is not in a particular range, and I'm hoping that helps keep the cord from getting tangled. Oh, 2 goes on the rack again. So yeah, force sensor, optical encoder, motor, H-bridge driver. We might throw some LEDs on there too, just to have some indication of what they're doing and maybe for fun. But that's pretty much the setup. Yeah, that's a bold Tuco. Alright, so I'm just going to demonstrate what I've got so far, and then we can start playing with it in new contexts. So I've got a little program that we can run on this Raspberry Pi, which I've just been using kind of for testing, but it's just a convenient thing that we can use to compile and upload the firmware and to mess with the packets going in and out. I've been starting to think about what the actual robot controller is going to be written in, and I'm pretty sure Rust is probably the right answer at that point, and I've been starting to learn Rust so that I can actually do that, but so far I've just got some little test programs mostly written in Python that run on this Raspberry Pi. So this one is just going to be reading the joystick state from this Xbox joystick, and I'll be using that to control this thing that I'm currently calling the velocity target, which is what I'm eventually going to be giving the winch-bot as kind of a nylon cord velocity that it's trying to hit. But right now I haven't actually written that control loop, and I'm just repurposing this as a kind of raw pulse width modulation value so that I can just drive the motor around. And then in the actual winch controller, those packets end up being received by this little function on what's effectively the Ethernet thread. And we just copy them if they're long enough into this buffer. So we just end up having this buffer that maintains the most recent commanded state that we got from the computer that's controlling us. And then every time this IRQ happens, this is kind of our main motion control interrupt that happens 250 times a second. So here we're reading the actual motion data from the optical encoder, and we'll be using this for the motion control algorithm later, but right now this is just to be reported back to the computer over UDP. Mostly what we're testing down here is this, which is letting us control the output of these 2 different PWM channels based on the number that we're getting from the controller. So control loop goes here, as the comment says, but right now I'm just kind of gluing this together without a control loop in between. And so we're actually taking these different paths depending on whether we're commanding the motor to run one direction, the other direction, or to stop it. And that's mostly just because it turns out the way that this pulse width set is written, if you set the pulse width to 0, then the output idles high instead of idling low, which is not really useful for us. So instead what we do is we're sure to so this is a motor H-bridge driver, and we want to drive the motor in one direction. We want to drive one terminal of the motor to ground, and then the other terminal we'll drive high some of the time and low the rest of the time. And then to drive the motor in the other direction, we just do the opposite. So there's always one output that's tied low, and then the other output that's generating a pulse width modulated drive signal. So in this case, we're just achieving that by turning off the output we're not using, setting a new pulse width, then turning on the one we are using. And in case it's off, then we just turn off both outputs. So pretty straightforward. So we can just use this Raspberry to make sure that we have the right firmware loaded. I think it's already compiled and everything, but we can just walk through the process of flashing it just in case. it would need to have power. So 5 volts for the microcontroller. It's drawing 150 milliamps. That includes the microcontroller and the logic power supply for the motor driver, and the A to D converter and the optical encoder. So all of that together is drawing a little, yeah, like 0.8 watts right now, 170 milliamps. So then we can flash it. Cool. And now if on the Raspberry Pi we run this telemetry script, now we're getting back a packet that shows us all the readings that this is taking every time one of those 250 hertz ticks happens. So if we spin the optical encoder, we can see a position, speed, and acceleration reading over there. The force sensor over here, if I press on this, you can see this number here is the force sensor reading, so if I press on this, you can see that increase, maybe? Well, that's decrease. Yeah, that's decrease, and that's increase. The two basic polarities. This is a count of just how many ticks have happened, period. And then if we start sending it commands, we should also get those commands echoed back, along with a count of how many commands it's getting. So that'll be this winch tester script. Cool, now the command counter is incrementing, and if I mess with the joystick here with the controller actually on, now you can see the value that we're commanding, and then it's echoed back in the telemetry packet right here. So, I guess we should look at this on the scope next. Yeah, Tuke looks pretty happy. And this is the motor with the slightly bent shaft that makes a decent benchtop demo at least. So the motor driver that we're using is it's from ST Micro, it's the L298D if I remember right. L298N. And it's a 2-channel motor driver. Currently I'm only using one of the channels. It actually has a configuration where if you only need one output, you can get double the current by bridging the outputs together. So I think that's what I'm actually going to do. That just isn't the case yet. So right now we're just using a single output. Let's get a ground. Carefully access this signal. Alright, I think I have the PWM signals plugged into both the Oscilloscope and the motor driver. The video from the Oscilloscope is going to be a little laggy the way it's set up right now. But that lag isn't actually happening. It's actually quite responsive. Let's try to get a better picture here. So this is starting at 0 control stick. If I press it in one direction, then I start getting pulses on one of the phases until it maxes out. And then I think I'm just not triggering on the other. Oh, I put the wrong scope probe on there. Let's try that. All right, so This joystick has a bit of a stickiness, so you can actually get it to stick in a position that is just outside the dead zone that I have set. That's what that was. If you actually have the joystick zeroed, then it'll be 0. And if you start pulling this down, then we'll get a little bit of a pulse until it maxes out. And the rate that I have this set to is 25 kilohertz. Can see it a little more clearly. Pretty good resolution too. This is a 16-bit PWM coming off of the main 120 megahertz clock. Way more resolution than we need. Robert is asking, is this an NFET plus PFET H-bridge, or is this 2 NFETs and a boost capacitor? I don't remember off the top of my head. This is certainly one of the ones where you don't, like, this microcontroller has a fancy enough PWM peripheral that I could certainly just attach my own MOSFET drivers to it directly and handle generating dead zone or dead band and all that. But in this case, the PWM driver is actually pretty simple, and it just acts like, this is the configuration that I'm going to be using it in. 2 inputs. These just act like high current push-pull buffers, effectively. There's the actual power stage. Hello, mouse. I don't see a boost pin or a bootstrap pin, so I'm guessing maybe it's PFET. Oh, maybe it's bipolar. Yeah, maybe it's bipolar. So not FETs at all. Yeah, I don't know. I mean, I'm not super attached to this particular motor driver. I just got them because they were commonly available and inexpensive and seemed like a good match for the motors that I have. Up to 46 volts. Yeah, each channel is rated for 2 amps, and then if I attach them together, I think I get 4 amps. Oh, I don't know if that answers your question. Anyway, enough waveforms, let's get this motor spinning. Alright, so I think all I need to do is crank on the 24-volt power supply. Alright, we have 24 volts. Check that out. Oh, I see. Robert was worried about maximum duty cycle restrictions. It's always a puzzle with Robert's comments. They're always like asking something that seems kind of tangential, and then you find out what they're actually asking about. But yeah, this is actually drawing pretty low currents, 270 milliamps or so. Of course, if I load the shaft, then that's like 0.6 amps. That's about as much as I can do without hurting my fingers. One thing I wanted to look at, well, so I still want to bridge the 2 outputs of this together. I'm also a little bit concerned about back EMF raising the overall supply voltage above what my inputs can handle. Maybe to demonstrate that, let's put the oscilloscope on maybe the motor phases and the power supply rails. There's still kind of an open question about whether the power bricks I'm planning on using for this are actually up to the task. So that's maybe something else we can test, assuming we get that far. I think the actual power consumption isn't going to be that high, despite the fact that theoretically I could peak the motor at a decent number of amps. but maybe that means I need like a bigger storage capacitor and maybe some transient absorption at the power input. All right, let's have 3 channels. Okay, blue scope probe just on the input power. And then I think it's potentially easiest to get these signals if we turn the board upside down. Alright, I'm not going to have the most amazing grounds here, but I think the signals we care about are pretty low frequency. Okay, so that's the scope on motor outputs and power inputs. Let's try that for now. All right, 24 volts on. All right. So we have power supply. And then let's give the motor a little bit of juice. Huh. You see that signal sinking below ground? I think that's, is that resistance in my wiring, maybe? Or, oh no, I had that channel AC coupled. That explains it. Okay, now everything is DC coupled. Much better. A little bit of bounce in the other side of the motor, but not nearly as much as I was seeing. All right, so now if I pull the stick, then you can see I'm starting to energize the motor. But then as I decelerate, you might have noticed that green trace kind of bouncing a good bit. Let's look at this at a different time scale. See that? While I was decelerating, there was some extra energy built up by the motor acting as a generator, and then that ended up going right back into the power supply. Which is great if you have a battery you can charge, but if it's the output of a DC converter that's just going to end up overloading, then that's not so great. So that cat in the chat was saying back EMF shouldn't push the voltage above the rails unless you have something else external turning the motor, but it doesn't have to be external. Like, the motor itself is doing this. It's just the inertia of the shaft. I can get the motor to jump by starting and stopping it fast. Let's back out and look at this on a different time scale again. So I'm being a little careful with this because I actually think I could probably break either the motor controller or my power supply by revving this thing up to full blast and then just letting it go. So, oh, what did I do there? I'm getting some noise in the brushes now. I think I might have just gotten the motor into a configuration where the brushes were especially noisy. That's interesting. Oh, power supply just detected overvoltage and turned itself off. So yeah, I think I need a solution for this. The easiest and laziest solution would be software only, just by managing how slowly I decelerate. But that has its own problems, especially for fault conditions. Like, you know, let's say you press the... So if you press the emergency stop button, I think you might actually be fine, because then you develop an open circuit, maybe you damage the motor controller, but at least you've disconnected it from the power supply, which is the thing that I worry the most about damaging. The motor controller itself can handle a pretty, like you saw on the datasheet, 46 volts. The capacitors are only rated for like 35, but... Peter says, so maybe freewheeling diodes are in order. There are diodes on the motor controller driver board, which is what's funneling the extra voltage back into the power rails. But then the problem is, where does it go? I need like a voltage clamp on the power supply rails if I'm going to dissipate this energy. And then Peter says you usually add capacitors on the supply voltage rail to deal with the spikes. I mean, I could just add a much bigger capacitor here. The issue is that that's relying on the capacitor to absorb all of the motor's energy. We could try that. I don't know if I have amazingly big capacitors handy for that, but I mean, I don't think that's going to help a lot. I think it's just going to kind of like squish that peak down a little bit on that blue waveform. I think you're still going to see the peak there. Then Mikhail is saying 4 diodes, 1 across each transistor of the H-bridge should do. But that's what we've already got. Like that thing that you're talking about is how you get the energy back from the motor into the power supply without damaging the H-bridge. We've got that. Now the problem is, what do you do with the energy once it's just on your power rails? Hey, Tuco. Well, we can try the capacitor solution because I might have some of those. I think maybe the real solution is to... I don't know what you use for clamping at voltages like this. I think this is above where Zener's are really good, but I might be mistaken. Maybe you can get Zener's that operate at like 28 volts or something around there. I think the Zener's don't kick in very quickly, so it would still go a decent ways above your power supply rails. The other thing we could do is just try attaching this to the power supply that I plan on using and just watch how that power supply deals with it. You know, does it adjust its regulation correctly? But I mean, still, even if it turns off its regulation entirely, it's going to have voltage building up on its output capacitors, which could be a problem. So, That cat says, with a regulated power supply, you only need to buffer enough energy to be slow enough for the regulation. Yeah, I mean, that is true. I mean, the capacitor is kind of racing. You know, it's got to be enough of an overflow buffer so that you don't break any of the other components in your output side of your DC converter. And Mikkel is suggesting some mean well supply. I mean, the supplies that I have are mean well supplies. I think they might be smaller than the one you're suggesting, but I mean, I'm aware there's a range of them. I just got the one that I thought would work because it was a good price and size and everything. I'm aware that there are other power supplies that exist. Oh, no, this is smaller. This one that you're suggesting is 1.5 amps. I think the ones that I have are... Fine, I'll just get the power supplies out. Yeah, 2.5 amps. Completely different. Yeah, no, this is maybe, I think, closer to what I want, and this is also enclosed. So this was a lot easier to deal with in the winch-bot situation than having a power supply in the bot that I had to make room for. So these are Meanwell, 24 volts, 2.5 amps output in a barrel jack. So, I mean, part of the question is just like how well would these deal with an overvoltage on the outputs, but I'm pretty sure the answer is not very well. Like, even if they would survive, that's not a nice thing to be doing for a power supply that isn't specifically designed for it. So I don't think we want to rely on that. Oh, are we missing the bottom of our chat? Oh, there it is. I'm just catching up on chat and trying to parse out the deluge of comment that people have for me all of a sudden. Yeah, isn't this what you just said before? Oh. Yeah, no, like, not the... You mean like computer power supplies? No, this is all 24 volts. No. So, anyway, let's think about that problem, but I think the first thing I want to get into is just actually let's hook this up to our actual winch mechanicals and see how this works together. Hey, Tuco. He doesn't care about any of this, he just wants to play all the time. All the time, he just wants to play. Okay. Let's turn that off. I know, Tuco. Okay, so I've got this little mess on the desk, which I need to sort of transfer, sort of reproduce. My little prototype over here has the plastic parts and the motor and the sensors all already mounted. I just need to basically replace these motors and sensors with those, and then we can try out that mechanical thing. All right. Let's just transfer this all over pretty straightforwardly. We have a motor output. Still haven't doubled up on this output, but we'll do that soon. I might as well modify this board to have the doubled up outputs and some kind of overvoltage protection all in one go. Oh man, I'm just trying to parse out the chat again. Peter says you may want to have separate supply paths for the motors and the electronics with a separate capacitor. You mean with like a diode to charge that capacitor, maybe? Yeah, I guess I could just catch the energy with a capacitor and a plain old diode. I was thinking about dissipating the energy with something like a Zener diode, but yeah, I mean, I don't have to dissipate the energy. I could just reuse it. I just, I mean, the other components I have on that rail besides the power supply are all just buck converters. So, like, I could just make sure that my buck converters can handle such a big spike and then put it all on one capacitor, but that seems a little dangerous. Having one capacitor just for storing the back EMF spike seems nice. So yeah, I'll have to think about that. I don't think I have all the right components to test that stuff right now, but I'll have to do some research and shopping and get some capacitors and diodes probably. All right, so that's the motor hooked up. Then here's the encoder. With its super long wire, which I'm definitely going to want to trim, but I'm not going to do that just yet. And this is just a little breakout board with pull-up resistors for each of the wires, which I'm not going to need this in the final design. I think I can just incorporate this directly into the little wiring harness that I make. And this has power, which I don't know the actual specification. It's probably designed for a pretty wide range of input voltages. It seems fine on 3.3 volts, so that's what I'm using it on. And then the outputs are open collector, so it pulls them low but not high. And then it's just two phases of quadrature. So they're kind of arbitrary. Swapping them just swaps the direction of the rotation that you're detecting. So there's the other encoder attached. Oh yeah, so Peter is saying the spikes that we saw aren't massive on the scope. That is also because I was intentionally decelerating it pretty slowly. I haven't tried just checking what the maximum kind of spike we can generate is. That might be something to do. That's probably something I'll do with... Well, I think I want to at least protect my power supply from that before I try that. So, but I have diodes, so we could at least like just hook a diode up to that and try it. And then worst case, we end up damaging the motor driver or its input capacitors, and that's probably fine. Those are cheap and replaceable, and I don't mind doing a destructive test on one of those if we need to. But the power supply is definitely not happy with the back EMF. Okay, so next is just the force sensor, and for that, that I will definitely need to solder. Let's just get that ready. Yeah, smoke and sparks probability, yep. Yeah, so I guess what I'll do is put this together with the spool and everything, because if we're going to get back EMF, it's going to be when we have it accelerated such that the entire momentum of the spool and the weight of the stuff that's attached to the other end of the winch, like that's all helping it continue moving, like that's going to be the most back EMF. I mean, the most back EMF would be if that can overcome friction and the motor just continues to spin, but I don't think that's going to be the case. I mean, you could effectively just convert all of the potential energy in the flyer robot into voltage in that capacitor. It's unlikely, but it's maybe something to plan for. Alright, so these are also pretty arbitrary. We have an excitation voltage, which is an analog power supply for the sensor, and that's the red and black wires. And then the actual sense wires, which is where the tiny voltage comes back for the A to D converter. And these are also arbitrary. We could swap them and it would just change the sign of the reading. But in this case, it looks like we have plus as green and white as minus. Oh, can I vise this? This might be a good use for a less sticky stick vise. Maybe a bench kind of vise. Hello, soldering iron. Spare sensor removed. It's not going to be the most amazing joint, but this will do for the current stage of prototyping. If you've ever taken apart a digital scale, you know it doesn't need to have high quality solder joints to work. Alright, there's that sensor board. That can just kind of hang out somewhere convenient. So everything investigated just to make sure nothing is going to short out when I apply the power. We have the sensor board, the breakout. I can take the debug connector off of this board for the moment. So we've got Ethernet for commanding this. We've got 24 volt power, 5 volt power, motor driver, H-bridge, pull-up resistors, A to D converter, and mechanism. Just gonna make sure my Xbox remote thing is still working. It looks like it is. So now I'm going to turn on the 5 volt power supply. And getting telemetry back. Let's check out the sensors before we turn on the motor supply. So here's our telemetry packet. There's our command, so we are getting data from the joystick. We should see that moving if we wake up the joystick. Yeah, there's the joystick data. Then we should have strain gauge, so if I actually physically move this thing, that's positive, and that's negative. Looks like the 0 position is somewhat negative, but that's fine. Like, the actual calibration is pretty arbitrary. And then actually if I pull on the cord here, I don't know why I was like reaching for the pulley and pulling it on it directly, but the goal here is that you pull on this cord and then it's measuring that. Great. And then you can also see the encoder moving around as I pull this. This column right here is the optical encoder, which is connected to this capstan down here. So I can spin that directly if I just reach in there. But if I grab this, then you can see it moves slightly. Oh, Mikey says that they'd love to see more arty stuff. Yeah, that might be nice. I think I'm getting over my fear of art these days. It was fun doing some of the LED stuff for the winches. I think I might, after learning a little bit more Rust, maybe do some kind of LED programming with Rust on stream. That might be fun. Alright, so I think we can just try this out as soon as I power on the 24-volt supply. Let's stop procrastinating. So I'm going to try to make sure to keep tension on this, because otherwise it can tangle. And I don't actually know which way is forward, so we're going to try one and maybe have to reverse real quick. Oh, that was the right direction, and it's fast. Wow. Whoa. Yeah, okay, that's fast. Whoa. I think the force sensor was a good idea. Let's get some alternate camera angles here. Whoa, that's a tangle. So I'm trying to unspool the cord. And there, oh, there it goes. Yeah, so it got tangled and then started reversing, but I think I got past that. So that's definitely something, and that happened because of my fast motion earlier that kind of jerked it around and got the cord caught. That's one of the reasons I'm excited about having the force sensor, is I can have the firmware basically lock out any motion unless the force is within some predetermined range. So if the robot has like a brief tangle or a brief bump or something and the cord goes a little bit too slack, it'll just stop moving until it's no longer slack. Oh. Mikkel says, what's the model number of the PSU you got? They're interested in looking at the datasheet. It is... So the ones that I got for the winches, which we don't have to use, but I'd like to. This is the Meanwell GS60A24. It's a 24-volt, 2.5 amp, enclosed power brick kind of thing. So I think the next step here is I want to actually mount this so that I don't have to keep moving this. Whoa. Yeah, I want to actually attach this to something with load on the end of it. So, a lot of this is still going to be connected to the power supply and stuff on my desk. So I think what I'm going to do is just turn that off and try to move this whole setup just right over here. So I've got this stool, which we can clamp the whole thing down onto, and then a lighting stand up there with a pulley. Reversing this camera a little bit. Don't entirely know where I'm going to want this. Let's put this here for now. I'm going to bring everything except the power supplies first. The cord for this encoder is still really long. So the way this is eventually going to attach is through an M8 bolt. I didn't actually have any bolts right now, so I'm just using shaft and nuts. Oh, Mikhail looked up the overvoltage protection on those power supplies and says that you have to power cycle it to get rid of the overvoltage state. All right, starting to feel sturdy-ish. Maybe I need to back this whole thing away from the camera a little bit. The main constraint here is that the power supply wires are not amazingly long. Maybe I moved the power supply for this whole setup. All right, let's move the power supply. We can just bring the power supply with us. Tuco. Sorry. Oh, heavy power supply. Oh, but it has this great feature where you can stand it up on the rear end, so I can just sit it next to this whole experiment. Alright, this is going to be slightly different than I planned, but probably better. Oh, Mikey's asking how much heat's coming out of that box. Tuco seems to love it there. I mean, I could ask my UPS how much power is going in, and that would be pretty similar to how much heat's coming out, and it's probably like 400 watts. power supply. Oh, this is one of those rare cases where vertical video would actually be slightly better. Everyone's like, no, don't do it. Yeah, maybe we go down. I should also maybe just put the camera on an actual tripod. Well, that looks workable. I think it just needs power and Ethernet and to have that cord hooked up to the pulley. This would be easier with 2 pulleys. I don't know. The geometry here is slightly different than it's actually going to be. I want to give the test weight a decent amount of room to go up and down, but I'm also trying not to rub against the edges of this. You can also see it trying to twist, which is a problem because I don't have the back plate made yet, which is going to hold it in that axis. So it might rub a little bit. I might have to tighten this also a little bit. Oh, I'm missing a nut. I'm going to tighten these 2 nuts against each other to keep this from spinning. I guess that's a thing that I might do. Actually tighten it. That's a little better. Yeah, that's a lot better. Alright, power. Maybe not with all the circuit boards sitting on a metal stool. I know all of you who were hoping for explosions. We're going to let that one slide. Needs a little bit of tape. You know, maybe I should just move this camera to a tripod. I feel like this is the worst of everything. There is a zip tie holding some of these cables on. Not anymore. All right, DSLR freed from the confines, soon to be reattached. Alright, I still don't have a ton of wire, but at least we can get a little closer and then I can set up a better, wider shot once I have the thing assembled. Getting the tripod legs extended. Okay, so Ethernet needs to happen. Two of these patch cables turn out to be long enough. Okay, We just need power. So first the 5 volts. Looks like we got telemetry. All right. And 24 volts. Bit of a spark as I attach that. Gotta charge up the capacitors. All right. I think it's just waiting for some PWM. So, oh, that's spooling out. Great. Let's maybe put some weight on the end of this. All of that noise is coming from the pulley. Alright, so for some test weight, I might just use my soldering spools over here. I think this is going to be a little over 1 kilogram. Let's measure it. .16 kilograms according to the scale. 1.14 maybe. So probably lighter than the actual robot, but not by that much. So then this, that's going to want to sit pretty much exactly where the robot is, but I'll keep them apart for the moment. Now, spool out cord. Oh wow. It's still spooling out. What just happened? It looks like it lost communications and it just continued to spool out after it got to a certain point. And then I just killed the power. What just happened? Are the batteries dying in my controller maybe? The LEDs looked a little dim. It looks like I'm getting packets through again, so I'm going to turn the power supply back on. And the motor is not moving. Let's try winding this cord back up. That's fine. Definitely a little scary having the PWM connected directly to this Xbox controller. That's not going to be the way it actually works. So I'm just taking up the slack now. Now it's starting to actually lift. Oh. So when I'm lifting, I am starting to hit the current limit that I have set at 1 amp on the 24 volt supply. So I might need to increase that a little. I'm only using one of the motor drivers right now, so let's set the limit to 2 amps, since that's what one of the drivers is rated at. So now we're limited to 24 volts, 2 amps. Oh. That's lifting it fine. And now I'm above that point. So let's adjust the camera angle a little bit. So part of what I wanted to test here was if I could, spool it in and out a lot and not have the cable tangle. So that might be something I could start to test. I'd really want that to be kind of automated so I can just run it for a while. For that to work, I need to be a little more confident in this thing's ability to run without breaking itself. So maybe checking the force sensors might be a good next step. And actually having it automatically run only if the force sensors are within range. Oh yeah, and as Mikkel points out, I'm going to have 4 of these sharing the burden of lifting it, so I expect each one to actually not be lifting a whole lot of weight, but you have some other things working against you, like the angles are not especially great. You end up having to lift not just the kind of, it's not like you're just lifting vertically, but you're kind of pulling sideways and then trying to lift something that's in the middle, so the efficiency is going to vary a lot depending on the geometry of the robot. So what is the power like? That's like 1.5 amps, moving at that speed. And if I max out the control stick, then I easily hit the 2 amp limit. Whoa. Huh. Yeah, I lost control of it again. And it was all the way up there with the pulley. I think that was the same thing. It seemed like it was responding. It was losing its ability to respond to the joystick. Let's just lower this a little bit to get some slack. It's still on. Let's put some new batteries in the controller and see if that fixes it. Why is Mikey saying the Xbox controller's been flat for a while? Oh, the flashing? I thought the flashing was because it didn't have a channel assigned, but I guess that isn't the case. I'd only ever seen it do the flashing. I assumed it was because it wasn't getting like an Xbox player number assigned to it because it was using the EVDev API. All right, so I can see this updating on the telemetry now, so I'm going to turn the power back on. All right, I think we might be all right. Oh, it's got a tangle. Does it? Something is scraping in there and I can't quite tell why. bend the shaft of another motor. I don't think that's it though. Let's try this with a lighter weight attached maybe. That ding. Mikkel says, "Do you have the source files for the winch-bot 3D prints?" I do. I've got them. I've got some version of them uploaded to GitHub. The latest stuff is in my Fusion 360 account right now, which I just need to export the latest stuff. But yeah, I've been trying to keep them up on GitHub mostly. This is maybe just enough to keep the line from being slack. Yeah, that sounds terrible. Oh, I guess we're gonna have to take off the cover and see what's wrong. Oh, there are wires all over the shop for this. Gradually converging on a good placement that'll help me get this stuff on film. On video. explains what happened. Well, I guess I found the weak point in that design. Oh, actually that was just the glue joint. The plastic didn't even break, it was just the glue. So definitely the design was putting way too much stress on that particular joint. And then there's a nice wad of tangled bleh. Alright. Well, how much of the drawing board do I go back to this time? I mean, that part's still fine. Alright, well, I guess that answers some questions I had. I've been a little on the fence about this winch-bot design. Like, I had identified several things that were not so great about it, but I thought it might have been enough to at least do some prototyping work. And, well, now I know where it's going to fail. And I think some of this is working out alright. Like, some of the sensor arrangement I think I might just keep verbatim, but I definitely need to rethink how the spool itself is held together and how it mounts to the motor. I mean, one thing I could try is just use like a better glue. Like, I think that was just super glue, and from the breaking pattern it looks like maybe it didn't make an especially great area of contact. And so I could try using an epoxy or something. I just didn't intend the design to have that glue joint be a load-bearing part, so now that this has brought that to my attention, I think I just would rather fix the design though. I should just unhook this. That goes well until like you get a knot going through the mechanism. But this mechanism actually seems to be working out all right. And in fact, we can maybe take a look at the telemetry to see how the feedback is working. I just want to untangle this a little bit more. Well, actually, you know, I could also just put another spool on here since I have some other spools that are already glued together. And I could put one on here just for testing, even though the design probably needs some rework. It's a little bit of wobble, which I think is coming from the way this is mounted. Yeah, I think that's coming from the mount. That's just attached to the end of the motor shaft for the set screw, and I think there's just a little bit of an angular inaccuracy there. Let's get the telemetry on the screen. So this is going to be a little bit raw, as you might guess, but this number starting where my mouse cursor is and going right is the force sensor, And then I think this number here, somewhere around there, is the position. And then next will be velocity and then acceleration. So we should be able to see those move around. Or you probably will be. I don't know if I'll be able to because I'll be farther away from the screen. Okay, well I can see the acceleration and velocity moving. I can't actually see the sign changing on the speed from way over there, but I'm gonna make this slightly bigger. I think when it just stops for a sec, I think that's the terminal app. Oh, you know what? It's acting like I only have one of the two quadrature phases because it's not detecting direction. Can we fix that? That might be something to look at when we have the Oscilloscope connected. I guess I can check which one it is by removing the pull-ups on each. So that one, no effect. Oh. That's interesting. I'm still getting counts even without either of the pull-up resistors installed. Alright, yeah, I'll need the scope to debug that properly. Well, what about the force sensor? From all the way over here, that seems to be behaving. Cool. Seems like the vector's right, too. Alright, so the screw is tightened. Since even if we know, well, So I know I need to do a bunch of CAD on this still, but it would be nice to get some data about whether this avoids tangles or whether I still have to worry about that. So I'm threading the cable or the cord through, and then tying a knot in this end. Now it's ready to wind. 24-volt power on. Let's get some of this out of the way. All right. So the direction is pretty much arbitrary here, except that is actually a little better. Oh, that wobble is terrible. Fix that. Not much better. Let's do a little more of that. Just adjusting the spacing between the spool and the mounting bracket. Okay, that's better. Right. Oh, that's just a beautiful design. Just every part of it works so flawlessly. Alright, maybe this is the end of today's video. I think this is about all the fail I can cram into this particular thing without setting it all on fire. I mean, I guess we did want to check how much voltage we can generate with one of these motors abruptly decelerating. Yeah, I think I might save that for a different time when I'm a little better prepared, though. I think this might be a good time to end this particular experiment. Oh, little winch. Yeah. Well, we've discovered a very rapid way of breaking these particular spools. Not quite as rapid as just throwing them off of something tall, probably. I'm wondering if it would be worth reinforcing one of these spools with epoxy and then doing this again just to do our tangling experiment. I don't know, so far I haven't seen any evidence that the tangling is going to be a problem. But I think I might need to think about this and go back to some drawing boards or two. Oh, on the bright side, we have parts of a robot. We have a rotating shaft and some sensors that measure a rope as it moves through some wheels. That part works all right. I think the next design, like part of what went wrong with this particular design is that I was trying to get away with having just one central load-bearing piece of plastic, basically, for all the axles to go through. And I think I need to redesign it so that it has two halves that are each load-bearing, like that piece, something that occupies a role very similar to what you're already seeing, and then another piece that would hold the other side of the spool, and then those two go together as one really rigid unit. And then around that you put like a much thinner shell that has like the nice looking plastics. I was trying to combine the thin shell with one half of the spool mount. So you can see that with the shell fully installed, it kind of worked, but then with the shell not installed at all, then it broke pretty much right away. Oh yeah, and so as Vavasor in chat says, the actual winching seemed like it was going pretty smoothly though, so that's encouraging. Yeah, I think so. I'm a little bit concerned with how much current the motors might end up using, but I think that as long as I keep the winch-bot pretty light, which has been my plan all along, I think I'll be alright there. But yeah, so far this seems alright. And, you know, like the mechanical design could use some work, but I guess that just means that I should be spending some more time CADing instead of fussing around with the firmware, which is good, because I think the firmware is doing all right now. It needs a PID loop still. I think I'm going to have the firmware try to control for the velocity of the cord rather than the absolute position, since I think that's going to be a more useful measurement for how I plan to actually drive this thing around. I think that the driving it around control loop is going to basically be, as I want to move the robot from place to place, I'll be giving it kind of proportionally controlled velocity vectors to each of the winches, and that'll kind of give me roughly the right motion, but then I'll also be adjusting that to keep the robot at approximately the same height. And that'll probably be something that I do using a variety of sensors. I don't know exactly how that algorithm's going to work out yet, but I can imagine a few things to start with, and a lot of it involves using the inertial measurement sensors and the LiDAR. Peter says, how about a longish spool? You mean something where it's not like super large diameter, but just like very tall and it like kind of winds across it? If that's what you're talking about, like that solves some problems. That decreases the maximum motor torque that I need. It means that I probably need an active mechanism to help wind the cord along that spool. Like I couldn't just rely on it settling into the right location. Mikey is asking if the sensor is staying true with the cord movement, any slip. It looks like it's fine. I can't really measure it especially accurately, but it looks like it was tracking pretty well. And then Richard is suggesting something metal. I assume you mean metal cord. I don't want the cord to be super rigid. I want it to have some compliance. So I know having super rigid cord makes it easier to measure things, but I think it also makes it easier to break things, and it makes it easier to sustain vibrations. So I'm actually pretty into the cord having some compliance. And let's take a look at that 2/2 pulley. So Physics Dude says, how about a main pulley designed in 2 perpendicular halves? Oh. I mean, what problem is this trying to solve? I mean, I think the problem was not that, like one thing that I could do is just like reorient the print to try to make the print itself not break in that particular way. But I think the problem I'm more concerned with is I don't want the print being responsible for holding that much strain in one particular place anyway. So like with this, I feel like depending on how you print this, I can't think of a way to print this where it actually makes the problem better instead of just moving the problem elsewhere. Since if you print it with each of these flat halves on the bed, then you end up with this thing where as the spool rotates, it keeps changing strength, and it has a weak portion of the rotation and a strong portion of the rotation. And so it's just going to rotate to the point where it's weak and then break at that time. So imagine your cord is pulling along this edge, and as it rotates, it hits a point where the force is totally parallel to that shear plane, and it just pops the two halves apart. I think you'd have a very similar problem. I just think it would happen in a different place. So I think ultimately what I want is probably to have my own shaft for this, and then to couple that to the motor shaft or something along those lines. So I think part of the problem is just that a lot of the force for this machine ends up just in this one little piece, and I think I probably want that to be something that isn't plastic. Michaela is suggesting to fill the gap with glue. I mean, that's how we ended up with the thing that just broke, because I made two things and glued them together and filled the gap with glue. I could use better glue, but I think we're still fundamentally going to have the same problem. How about this design? So the motor goes up here. Well, I don't know how to separate these parts in this diagram. Is the contact area between these parts just this little ring? And where does the bearing go? That's the hole for the motor, or does this need a shaft? I'm confused about how this design works. Peter says they're thinking like a car winch. I thought car winches had to have like a mechanism for moving the cord side to side. Let's take another look at that. I don't know if designs like this are just intending on the cord kind of stacking up on its own, or if it actually has something that moves the cord side to side. I mean, I looked at car winches when I was designing this, because that would have been one of the obvious solutions. The problem I saw with car winches is that they were all way too slow. So oh, okay, you respool the cable manually. Yeah, and this is true. The reason my pulley was concave is that I wanted to try to help the cord stack more neatly. My inclination is to make the pulley stronger rather than changing the shape like this. I mean, the root cause of this is that it's just weak in a way that I didn't even consider. So it isn't that, like, I thought about making it strong in that part and failed. It's just that I forgot to make it strong in the way that it failed. So I think the problem is more like I just need to take that particular part of the design back to the drawing board a little bit than thinking about angles and stuff. And I mean, this isn't the first problem with the design. There's other stuff that I also really needed to fix about it. So I think this is just like yet another nail in the coffin of something that I was already unhappy with. Mikkel says that in their design where the piece is attached, there's a lip. Can I turn off just part of this? Oh, that. I see. Yeah, I mean, so this design is, like, I see what you're doing. The reason mine didn't do this is that I needed a bearing in there. Like, I needed space for a bearing. But I see, like, in this design, it looks like you've just designed the whole thing to work with a single straight-through shaft. So, yeah, I mean, this is probably closer to what I'm going to end up with for the Tuco Flyer. There's just a lot of other stuff that I've got to think about at the same time. Like, I also need to think about how this mounts to the overall enclosure. I need to think about coupling it to the motor shaft. I need to think about just overall how big the whole thing is going to be and the center of gravity of the motor and lining up the exit of the winch cord with the shaft of the mount and just all these things. So, I mean, if I seem unenthusiastic about any solutions that you have to, like, a single problem from this, it's probably because I'm trying to think of the entire design. And the particular piece is like, yeah, this is fine on its own. This doesn't really tell me that much about how the rest of the design works, so I need to think about that too. Also, I don't know, these corners bother me slightly. I don't know if that's actually a problem though. Anyway, I think I'm done with this. Enough of that for today. Well, not enough of it for today, enough of it on camera. Enough streaming. I hope that was interesting. Thanks for tuning in, and I'll see you all next time.